Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different.
Quantum computing was pioneered by Paul Benioff, who designed a quantum mechanical model of the Turing machine in the early 80s. A probe into the nature of quantum computing by Richard Feynman and Yuri Manin suggested that quantum computers were able to do things ordinary computers simply couldn't, and the first quantum computer was proposed. The following was revolutionary in scaling the mainstream appeal and interest in what was till then a very lucrative topic. In 1994, Peter Shor devised an algorithm for the prime factorization of integers that had tremendous cryptographic significance. Shor's algorithm, as it was called, could break numerous public key crypto systems, including RSA encryption. In roots at the time, it took a classic computer. The quantum computing revolution was here. Well, not exactly. There are limitations to quantum computing, practical difficulties that are hard to resolve but even harder to avoid. First, let's dive into what gives quantum computers the edge over their classic counterparts, the basics of this so-called quantum supremacy. Well, a classic computer stores information in the form of a bit. Think heads or tails on a coin. Now, let's imagine we don't know the state of the coin. We can only estimate the probability of it being in either state. Sort of like a coin while it's spinning. In technical terms, this allows us to assign probability vectors representing all the possible configurations of a particle's state, letting us store more information. The more configurations, the more memory capacity we need. To mitigate the need for classic computer memory, which would soon become insufficient, we store information in quantum states of matter and compute on this information through quantum logic gate operations. But alas, there's a problem. As one paper put it, almost any interaction of a quantum system with its environment, say an atom colliding with another atom or stray photon, constitutes a measurement, and measurements turn our qubits into binary bits. This process is called decoherence, and to prevent it, we would have to quarantine the system from its external environment while still being able to compute on it. Decoherence becomes a large problem when we want to perform large calculations. The threshold theorem states that if environmental noise can be kept below a certain level, it will always be possible to correct noise-induced errors faster they are created. This suggests that fault-tolerant quantum computers are theoretically possible, but just because something works in theory doesn't mean it's doable in practice. Well, I guess only time will tell what the future holds for quantum computing. Thank you for watching.